Hi, welcome everyone. So, okay, so this talk is going to be about snarks, which are proof systems that are non-interactive. They are argument of knowledge, they are succinct, and they are zero knowledge. Actually, sometimes they might not be zero knowledge if they are respected. So specifically, this talk is going to be about lookup arguments, which are a specific kind of snark. And to talk about lookup argument, I first have to introduce the notion of vector commitment. A vector commitment is like the name; it's a commitment to a vector. So imagine you have your data set with you have a bunch of data in the column A. What you can do is that you can commit this data. You obtain a value C of D. That's going to put it like. And this commitment is going to be binding, succinct, hiding, or maybe not hiding. But the fact that it's succinct means that the commitment makes sense even if it's not hiding. So now, what is a lookup argument? So imagine that you take some element of the column A, for example, C, Control B, you pass it in column D, then you commit to the column D. You get another commitment, the commitment to the subvector. What a lookup argument allows you is to prove subvector D is indeed a subvector of the table A on the left. On your left. Good. So, very brief state of art. The state of art, at least the most efficient scheme we have right now. One is CQ by Egan, Davidson, and Fiore. And this scheme uses a technique of cache culture. Then there is this of Setti, Thaler, and Wabi. And the difference between these two papers is that Lasso works for a subset of all the possible tables. Some facts. If you didn't get it before, lookup argument allows to prove that F committed as C of F is a subvector of a table T committed as C of P. The interesting fact of a lookup argument is that the proving time is independent of the big table T. So it's independent of capital N after some precomputation. So here, for application, usually we assume that T is much bigger than F. Then, since we need some precomputation on T, usually what we assume is that for application is that T is fixed. And then we need to use vector commitment, but actually this Q and Lasso, they both use vector commitment based on a KCG, which if you want to commit to a vector, what you do, you interpolate the polynomial, and then you commit using our polynomial commitment. So what are our contribution from this paper? So the contribution is that we improve over CQ along three directions: efficiency, zero knowledge, and flexibility. I won't be able to talk about flexibility, I think. We extend the notion of lookup argument from vector to matrices. And then we give an application of matrix lookup argument to privacy preserving machine learning, which we call zero knowledge decision tree statistics. Okay, first bit. Okay, if you want to understand CQ, CQ starts from this ABOC logarithmic derivative lemma, and this lemma say the following: if you have a F that is a subvector of D, this is a subvector if only if there exists a sparse matrix M such that the rational function on the left is equal to the rational function on the right. As you can see, the rational function on the left is a sum over I from 1 to capital N. So it's definitely not independent on the side of the big table, but the fact that M is sparse does that many of these items are going to be zero. So what does Q? Some point of the protocol, there's going to be a random challenge from the verifier. It is going to evaluate this rational function on this random challenge, and it's going to interpolate two polynomials, A and B. A interpolates the addends of the sum on the left, while B interpolates the addends of the sum of the right. Pictorially, you could imagine A being on that circle and B on that circle. The reason is that when we interpolate, we use a subgroup of the field for the interpolation because we want to use later a sum check protocol, the Aurora sum check protocol, and to do that, we need to interpolate it on a subgroup of the field. So here, where CQ use much of the technique of CQ is the fact that this cache quotient technique allows to give a proof for the sum check protocol in a time that is proportional to the sparsity of A, and therefore independent of capital N. So what CQ does is that you need to run two sum check protocol, one for the sum of A, one for the sum of B, and then it needs to check that these two sums are the same. And I stress that here we need to run two sum check protocol because A is interpolated over a big subgroup, while B is interpolated over a small subgroup. One of the contributions that we give, the way we improve CQ, is to notice that if the subgroup where B lies is a subset of the bigger subgroup, then there exists a polynomial Z, and this polynomial Z is sufficiently computable, such that in some sense you can take the interpolation of B and you can move it from the smaller subgroup to the bigger subgroup. So if you take the polynomial B times Z, what you get is that this B times Z interpolate the same points, of course, in different, the same values in different points. And moreover, all the other points that are left blank, they evaluate to 0, which means that if you do then a sum over all the points, then the sum remains invariant. And this is one of the tricks that we use. Thanks to this trick, we can now do one sum check. I mean, we can do a batch sum check. So we can reduce the group size. And actually, thanks to this, we can also use technique from a zero-knowledge sum check from Luna, from a paper from Campanelli et al. And thanks to that, we have an easy life to get fully zero-knowledge, which is something that we define as being zero-knowledge, not only with respect to the smallest subvector, but also to be zero-knowledge with the containment with the big table. Okay. Yet some other improvements, actually using some extra tricks from a paper from Litmas, Hilm, and Zajan, we can actually have even shorter proofs. Okay. So now I can go to the second part, which is about matrix lookup. So the idea of matrix lookup is quite natural. Before we were committing to a problem. Now let's commit to the full table, the full data sheet. So we can commit to the full data sheet. And now imagine that you want to define a notion of submatrices for this. The easiest notion that you can come up is selection of the row of the data sheet. You copy them and you pass them on another data sheet. You commit to it. And then what you would like to prove with the matrix lookup argument is that the commitment to the sub-matrices is indeed a sub-matrices of the big table. So I guess this is quite natural. How do we obtain that? A couple of points. So we show a generic compiler that use any homomorphic vector commitment. And homomorphic vector commitment, you can read it as XG. Construction of matrix lookup argument for homomorphic vector commitment. The idea to commit to a matrix is to commit to the vectorization of the matrix. So you take the matrix, now you do a vectorization by stacking the columns one on the bottom of the other. Now you have a vector, and then you can commit this vector using your vector. And then our scheme works. First trick that we use is that we notice that actually, if you want to do matrix lookup when the number of columns is very small, say 3 columns, then things are quite easy to do because just use some tricks of some batching tricks. You hash the 3 columns together, you get one vector. So for 3 columns, it's going to be easy. For multiple, we need to do some extra things. So what we need to do is to so what our proof system does is to prove that there exist 2 additionally 2 auxiliary vector, a vector R and a vector C, such that if you consider the matrix R, C, and then the vectorization of this vector F, this matrices is a subvector of the matrices that is of the form I, J, T out J. This is the first thing that we need to prove, and we can prove it using our inner lookup argument. And then the second thing that we need to prove is that the vector R and C have a specific tensor structure. Basically, this means in this example means that the vector R should be of the form 4, 4, 11, 11, 11, 11, 12, 12, 12, and so on. While instead the vector C should be of the form A, B, C, D, A, B, C, D, A, B, C, D, and so on. This is the only extra thing that we need to prove on top of doing a lookup argument. And this is our easy things that we can prove using snaps, some easy techniques. Okay, so last part of my talk is going to be the application of matrix commitment to zero-knowledge decision tree. So here, the model is the following. So imagine there are these 3 parties. There is a model provider, there is a server, there is a client. The model provider knows decision tree T, and it commits to it. I don't know, send it from the cloud or something. The client gets to see the commitment. Then in the second phase of this protocol, the client can send an input to the server, X, and the server can send T of X and approve that why it is indeed T of X. It's kind of the simplified model that we look at, but actually the actual model is a bit more actually. So the client can send not only one input, can send a small n number of inputs. So we can send one n. The server will compute a function f over xi, or I from 1 to n, and approve that this is indeed so. And the thing that I'd like you to remember about this part would be that the efficiency of our scheme is theta of the size of f in terms of a circuit plus the number of inputs that are sent by the client times d, where d is the depth of the decision tree, while previous work had to the total number of the number of nodes of the decision. And these 2 values can change a lot. The second thing of our scheme is that it's universal, meaning that the function f can be whatever function you want, and you do not have to run a new setup whenever you want to compute a new function. Okay. So a couple of sentences on how we do that. So the way we do that is that we notice that actually a tree presents on the left a standard way to encode a tree, a decision tree as a tree. But actually, if you take a decision tree and you look at the hypercube of where all the inputs of the decision tree belongs, the decision tree partition is hypercube on boxes, what we call boxes. So here the example is quite easy. For example, if your input as x minus then 3, then you will land in this box here. So what you need to do to describe 3 is to describe all the boxes. Now, to describe all the boxes, you just have to have a couple of coordinates, fortunately. So you need to have a couple of coordinates which describe the box and the label associated with this box. So the label here, the sparkle is associated with the label of the first node, which is associated with the first box, for example. So now you put all these boxes one under the other, and you have your matrix. And this probably already tell you what's going to be our technique. So to commit to a decision tree, what we do is that we, from the standard encoding, we define box encoding, which is a matrix. And then we use our matrix commitment. Now, improving phase, for example, if the prover wants to show that 4 and 2 is equal to red, what the prover should do is go to the box where 4 and 2 belong, which is the label number 2, the nodes number 2. It select this row, it commit to this row using a matrix commitment, then use our matrix commitment, the matrix compartment, to show that indeed this row that I'm committing to is indeed a box, a valid box inside of the decision tree. So it's a sub matrix of the matrix that describes the decision tree. And this is the first proof. Then another proof, which is basically a bunch of range proof. He has to do one range proof for each dimension. And he has to show that 4 and 2 belongs inside of this box. And then it has to show some other property, for example, that the label is equal to red. But the second part of the proof is easy and is independent on the number of nodes. This first part is use the matrix lookup argument, and also in this case we are independent on the total number of nodes. Okay, there is a simple attack to the scheme that I just showed you, and the attack works when the model provider is malicious and it doesn't commit to a decision tree. If it don't commit to any kind of matrix, it means. So not all the matrices represented by the matrix encoding. Malicious model provider will commit to a matrix where there are two boxes. They are the same boxes, but they are labeled with two different colors. Now the server would prove that T32 is equal to. We can also prove that the evaluation of the tree on the. We saw that, so there is a generic fix, is that proving zero knowledge that the commitment is a commitment to a valid box encoding. Now, some commitment to a valid box encoding, this line cannot be there, right? Actually, we wanted to have some information. So what we came up is a set of algebraic equations that define what is to be valid box encoding. Constraint and constraints for validity. And actually, we using some new technique from a paper by Takahiro, which is called Matsuda. The generic snark that use algebraic constraints and go from square n to theta of n proving time. So it's actually quite fast. And as you may imagine, to square log stuff on the drug, but just to COR, a generic compiler to matrix lookup, and SNARK for decision tree inference and statistics. Thank you.
I'm just wondering if you could elaborate for people on what do you zero knowledge means? What was the created to?
Okay, well, zero knowledge is something that we define. So, respect of the table and the subvector, because in the formal way we define argument, the table part of something that is called the index, and the index is completely anyone can look at the index. The index is measured on it as a big table. So the index is a verifier can see the index. But if you want to be zero knowledge with respect also of the index, you need to have like a stronger notion, which is what we define. Basically, if you take the notion of lookup argument and you want to just say, let's use the standard definition of zero knowledge, then you would be zero knowledge only with respect of the subject by design. We improve it just because we want that for the application of matrix lookup argument, where the big table is what we want to protect, well, extra zero knowledge from. Thank you for the question.
We should move to the next talk. Let's continue again.
Maybe try to get into. Just change the URL.
Just click and change the
And
URL.
then it's slides.pdf. Go to. Yeah. They all set up from PDFs by default, but I need to do this. Sorry, it's very scientific.
The oblivious accumulators. It's going to be given by Joanna. It's a joint work with Fontaine by DMC and Srinivasan Raghuraman.
Welcome.
Thank you. Thank you. Yeah, this is work with my PhD advisor from George Mason and my collaborator from Visa Research from when I was at Visa Research. And before I talk about oblivious accumulators, even before I talk about accumulators, I would like to talk about sets and show you why we use accumulators. So if we don't, consider we have a set, and on the right side, we want to verify that an element is in the set. And we will need to store the whole set. And then, depending on how we organize the set, we would have to have expensive lookup operations or expensive updates. So this is when we use accumulators. What they do is, instead now we push the computation on the prover side. And we have proofs of membership. Sometimes we call them witnesses. So we have a prover, they send over a witness to a verifier. And the only thing that the verifier needs, similar to before with vector commitments, they only need this C set commitment or digest or an accumulator in order to verify. And ideally, most schemes, when an update happens to the set, they have efficient updates to the proof and the commit, and we don't need to recalculate any of these values. So an accumulator is a compressing set commitment, has a short digest, short proofs, and fast updates. That was the efficiency properties. We have more properties in terms of the functionality. Very briefly, we can have some trust, like a manager that uses. Sometimes we have no trust. We call this a trustless accumulator. These are the accumulators we use in blockchain to make the blockchain stateless. We can have an additive set. We can have a dynamic set. It has both additions and deletions. And then we can have membership or non-membership. Sometimes we have both. This is what we call a universal accumulator. I will use this term again. And the scope of this work is to see what happens with the other property, that is privacy. Privacy, we already have some privacy notions around. One is zero knowledge proofs. So what zero knowledge proofs do in this setting, in the accumulator setting, is they protect the prover from leaking any information to outsiders. And in this case, an outsider would be that verifier we talked about. So the goal is with zero knowledge proofs to hide the element and the witness. And we have works that do that for specific accumulator constructions efficiently, the RSA and the linear ones. And then we have works that do it for batch proofs. They hide the elements in the proof. Another privacy notion we have already is zero knowledge sets. This notion has to do with set privacy against outsiders. An outsider, again, is the verifier. And here we hide the whole set from the verifier. So imagine that the verifier can see the accumulator. We would like them to be unable to infer anything about the set. It's okay if they can know for this specific security goal, zero knowledge sets. And keep in mind that we can also combine those to know privacy. And we have also works on that. The idea here is you usually add some randomness and try to not let it interfere with the set, so you don't break soundness. And what we talk about in our paper is a new privacy notion that we call oblivious accumulators. And this time we want to see what happens with privacy against insiders. An insider here would be the rest of the provers, the rest of the entities that have elements in the accumulators and maintain proofs. So our goal is to hide everything from other provers and also from the verifier. But that is inherent in oblivious accumulators. And when we hide everything about a specific element, we also have set privacy for free. And as before, we can also have proven privacy with zero knowledge proofs, so that's orthogonal. And what's out there in terms of this notion of privacy against insiders? We have some examples that come from private transactions. For example, we have Zcash. It's an anonymous cryptocurrency. And what Zcash does is when they add elements in their state, they kind of commit to them, they don't reveal them. And when they want to delete, they just reveal a serial number that is unique to this specific element. Anyway, they do these techniques, but I will argue later that they don't hide everything because they leak the size of the set. Another example is Kiss. It's again another design of anonymous cryptocurrencies. When they set as an input, they run a permutation, they re-randomize the elements or the commitments to the elements, and they have to give also a proof of correct computation. But what you output is again a new version, re-randomized version of the set. So there's no compression here for this solution. And our goal is to achieve this full privacy, also have compression, and hide the side of the sides, the side of the set. So we call that oblivious accumulators. I'll show you how we define them and what security properties they have. So this construction, generic construction I'm going to show you is in the trapdoor lens setting. It can support a dynamic set. It only supports membership. And of course, we're going for privacy against insiders. So this is a very standard set of accumulator algorithms. First one is the setup. Then we have 3 algorithms run on the prover side. We have element addition, deletion, and these fast updates, proof updates I talked about. These are very standard, nothing changes so far. For example, when you add, you have this capital U information that is the state we need to store. And then you add an element, you add the new value, a message U, that is the update. And then when you want to run this memproof update algorithm, the extra thing we consider here for oblivious accumulators, and that implies that only the entity that added an element stores this secret information, and they can later delete only this entity. And of course, prover privacy again is orthogonal. So in terms of privacy properties, first of all, we have to hide the element. And that's easy to do. We choose to, at least in this presentation, we will represent, instead of adding the element, we will add a label that has to do with this element. I will call it LX add. Maybe it's easy to see that this is not enough if we want to hide everything, because similar to the Bitcoin case, even if you have this, even if you cannot see the element, you can trace the element according to the operations, if you follow the operations. And here it's a set, so the operations are addition and deletion. So in order to avoid tracing, we move to the next privacy property, which is add, delete, and linkability. And how you can do that, you can have a different label this time. Hopefully this cannot be linked. And you can call it del. And you can use, this is what Zcash basically more or less does. You can use a set for additions and another set for deletions, which, and you can add these different labels. And then a membership witness would be a membership witness of an addition label in the first set, non-membership witness of a deletion label in the second set. As I said, this is similar to the approach that is taken by Zcash. And here we'll argue that it's okay for cryptocurrencies to reveal the number of the coins in the system. But sometimes we might have these elements could be assets or could be users. And sometimes we would like to hide this, this size of the set. So you can see here that anyone can infer that if you the element right now accumulated is one element. And in order to avoid that and be able to hide the set, we have this third property called add, delete, indistinguishability. And basically we do the same with the labels, but we add everything in one set, one data structure. And membership looks like before. And here, if we craft these labels in the correct way, you're not able to tell if it's one element or if these were three additions and you have three elements in the set. And 1 and 3 imply 2. So using these construction ideas, we can further realize this construction, and for privacy, we choose to use a random oracle, and for the addition labels, we just use #1. For deletion labels, we use #2 in this example, and these go to the update messages, and hopefully they won't leak anything. Actually, we prove that they don't leak anything. And then as an auxiliary information to add this, to avoid like guessing attacks, we just add randomness. So here in the addition, whoever adds an element, they have to store the auxiliary information. Use it to delete later. And you can see in the paper why it's element hiding and satisfies add, delete, indistinguishability. Now, if we take this, the next property we're going for is compression. So we can take these elements, these labels, and add them to a universal accumulator, because remember, we need both membership and non-membership for additions and deletions. Or if we need to represent more information, we can use this as these labels as vector commitment, and then use also values or tags as the extra information if we want them to be updatable. Since you can add anything with this randomness and no one can tell, this construction allows for adding multiple elements, one element multiple times. So we suggest that if someone wants to make the accumulator to accumulate only unique elements, we can use a verifiable oblivious PRM. Mapping is unique, but this one takes some centralization. So in the paper, we give like a construction from key value commitments, and we show how to construct the key value commitment from accumulators and vector commitments that are weaker primitives. And the last thing we talk about are communication bounds. And in terms of accumulators, communication bound state that I mentioned. And this is what you need to store in order to add and delete. And basically denotes how much of this information, small u, we have to keep as a state. So we give two results, one for when you have add, delete, indistinguishability and you hide the set, and one for when you don't. Basically, what the result says is that if we want our commitment to be constant, as you here state, we have to keep increasing it with the number of operations. And the proof follows previous results about plain accumulators and communication bounds. Basically, the idea is that if you delete a fraction of the elements, you will need n bits of information, because your proof would need to be able to extract these elements for soundness reasons. And here, because we want to have indistinguishable operations, all our sequences of operations need to be the same as this scenario I mentioned. So all of them have to be of size n. And that is not exactly the case. for when we only aim for add, delete, or linkability. Here, the space could be a little smaller, and it has to do, like it's called del space, we call it del space. And it has to do with all possible consistent sets of deletions. So here we would like to hide the sequence among other sequences that are valid and consistent. It means they have the same trace of operations, but not among every other possible sequence. And yes, that was the results, and I will conclude with some open questions. One is, I only talked about membership. What happens with non-membership and oblivious accumulators? And it sounds a little like intuitively it's hard or impossible to show that an element is not in a set without knowing the set. So that would be nice to prove formally. And also I talked about centralization if you need to enforce unique elements. It would be nice to see if that's necessary or if it could be relaxed. Also, it would be nice to see if those two are related, if you need like unique elements in order to support non-membership, and what are the minimal assumptions you need in order to have non-membership and unique elements if they're connected. That was all I have to say. Thank you so much, and I'm happy to take questions.
Say no twice.
In any accumulator, if you add it twice and delete it once, it's still there. It doesn't break soundness because technically you added it once, but maybe from the application point, it's not very useful.
Thank you, Ioana, again.
Hello, I'm Takahiro Matsuda, and I belong to AISD Japan. So let's go to the advanced crypto session. Okay, the first talk is witness encryption for succinct functional commitments and applications, and the authors are Matteo Campanelli, Dario Fiore, and Hamid Reza Koshakra, and Dario will give a talk.
Yes, so thanks for the introduction. So I'm Dario Fiore from India Software in Madrid. So I'm glad to present our work on witness encryption for succinct functional commitments and applications. And this is a joint work with Matteo and Hamid. So let me recall the notion of witness encryption as proposed by Gargetto in 2013. So the main idea is that this is an advanced encryption system that allows to encrypt a message with respect to an NP statement X in such a way that anyone who holds a witness for X can decrypt. So more precisely, this means that when you encrypt, you can bundle the message together with the NP statement X, you produce a ciphertext, and then a decryption, you would plug a witness, and if this witness is a good witness for X, you recover the message. That's a correctness property. And instead, if this statement is not in the language at all, so there is no witness for it, then the ciphertext leaks no information on the message. And I mean, I'll keep it informal, but this is defined in with a semantic security style definition. So what do we know about constructions of witness encryption and its application? So the good news is that we do have candidate constructions of witness encryption for all of NP. These have been proposed based on AV tools such as indistinguishability obfuscation or multilinear maps. And it's also good to know that this is a quite powerful tool that it is known to imply like primitives such as public encryption or advanced forms of encryption like IB or ABE, and even sophisticated applications such as two-round MPC. So On the other side of the spectrum, we actually knew for many years very simple witness encryption system for simple languages such as linear computations over prime order groups under the name of smooth projective hash functions. And these can rely on lightweight objects, but they also imply that like simple functionalities such as CCA secure encryption or password indicated key exchange. So the question that we ask in this research line is, can we enable sophisticated applications by using witness encryption that are not as powerful as for all of MP, but maybe for some weaker functionality or for some simpler language? And to dive into this question, I'm going to pick one motivating application, which is what we did in our work. And this application is to round MPC. So for this application, we actually know the result by Gordon et al. That proposed how to use witness encryption for all of MP in order to build two round MPC from any n round MPC. But remarkably, in 2020, Benoit Libert showed a construction of two-round MPC based on a weaker notion of witness encryption called WE for NISIC of commitments. And they realized this primitive from linear groups under the decision linear assumption. And they even obtained a more powerful notion of two-round MPC called multi-party reusable on interactive secure computation. And I'm going to expand on what this is. And this has been dubbed shortly as Mr. NISIC. So very shortly, what we do in this work is to enable a more powerful version of Mr. NISIC, which is succinct. And we do it through a new WE notion called witness encryption for functional commitments that we define and construct in this work based on linear groups but however under strong assumptions that eventually rely on the GGM. Okay, so let me now give you a very short recap of what is multi-party computation. So this is a cryptographic protocol that allows several parties to jointly compute the functions on their inputs in such a way that the privacy of their inputs is preserved and their correctness of the computation is also guaranteed. So a major research goal in MPC is reducing round complexity, because especially if you're running with several parties, you would not want to have them exchange many messages in many rounds. So what do we know about this? So actually, while for general computations, you may require a lot of rounds of interactions, there has been fundamental results that have shown that actually you can compile any n-round MPC into a two-round MPC. So this has been shown by Garg et al. Using I/O and then later refined by Gordon et al. And based on this result that I mentioned that uses witness encryption for all of MP. One can ask, can we reduce this further? Can we get one-round MPC? And unfortunately, this is not possible, because if such a one-round MPC protocol would exist, then you could mount residual attacks. Essentially, you can use this single round as an oracle to leak information on other people's parties. So, however, in order to kind of work around this impossibility, Benoit Libert proposed this notion of Mr. NISIC, which is a two-round MPC with a reusable first round. So the idea is the following of their notion. So in round one, what parties do is to commit to their inputs. They just do commitments of their inputs. They don't know which function they're going to compute. And they post these commitments in a bulletin board to which everybody has access to. In round two, when you know the function you want to compute, maybe on a subset of these inputs, what you do is to, every party locally computes a message, alpha, that is an encoding of the function, the commitments of the inputs that are supposed to be involved in the computation, and your local input and opening of the commitment. Okay, so you just broadcast these alphas, and then with only this information, you can reconstruct the result. So that's a very nice paradigm, because once you fix the first round, so you have fixed the commitments to the input, you can execute round two as many times as you want on different functions, different subsets of parties' inputs, and so on. So it's a very flexible model of MPC. So Benoit Libert, as I mentioned before, showed how to realize Mr. Nizik using a weaker variant of witness encryption called W for Nizik of commitments. And they use this in order to essentially realize this round collapsing technique. And I will not enter in how this is done. But what is this W for Nizik of commitment? So it's a witness encryption that is for this specific language that says, so you can encrypt to respect to a statement that consists of a triple, which is a commitment, a function G, and an output Y. And this triple is considered in the language if there exists an input X and an Nizik proof pi that certifies that Y is G of X and that this is a commitment to X. So they realized this from the decision linear assumption. The construction approach essentially was to take a variant of Groth I proofs and commitments in which they stripped out the quadratic part of the verification. And then they combined this with smooth projective hash functions in order to obtain this W for Nizik. So what we do in our work is to focus on an efficiency aspect of their construction. And our observation is that in order to deal with this language, they had to rely on statistically binding commitments and statistically sound Nizik proofs. And this has an implication, which is that commitments must be as large as the input size. And also like the size of the proofs, and so the W decryption time has to be linear with the input size as well. And this has an impact in the Mr. Nizik construction because if these commitments are statistically binding and long, when you post them on the bulletin board, with this bulletin board grows with the data size. So especially if we think of a bulletin board as just a set of pointers to data that has to be used multiple times, this is not really desirable. So the question we ask is like, can we have a succinct round one? Can we have like a round one in which what we post in the bulletin board are just commitments whose size is independent of the input, so they are short, so that bulletin board grows only with the number of commitments times some fixed polynomial in the security parameter. So, and to explain our solution, I have to first recall you this notion of functional commitments that was proposed by Libert, Raman, and Jung in 2016. So this is a cryptographic primitive that allows one to commit to a large vector X in such a way that later you can open to a function of this vector. So you can essentially create an opening proof for f of X that you can verify given only the commitment, the description of the function, the output, and this proof. And functional commitments have two crucial properties that are that the commitments are short and the openings are short. And by short, we mean like, for example, logarithmic or constant in the vector size. And in terms of security, they satisfy evaluation binding, which roughly says that you cannot, it is computationally hard to open one commitment to two different outputs for the same function. Okay, so what is our notion of witness encryption for functional commitments? So the idea, this is quite inspired by W for Nizik of commitments, and it is that you encrypt a message with respect to whoever holds an opening for a functional commitment opening for G of X. So more precisely, a W for FC is an extension of the functional commitment algorithm with two additional procedures that for encryption and decryption. So when you encrypt, you take the message and then you take a function G, a commitment, and an output. And with this, you can produce a ciphertext. And then, like decryption, requires to know an opening proof with the property that if this opening proof satisfies the verification algorithm for this G, CM, and Y, then you recover the message. But if the commitment is a commitment to X, but Y is not G of X, then this message is computationally hidden. So in the sense that you cannot distinguish if you, for example, encrypt an N0 or N1. Okay, so what are our contributions in this paper? So we propose a definition of W for functional commitments. So this is very similar to the one of Benoit Libert of W for Nizik of commitments, but we had to deal with some definitional issues related with the fact that in our case, commitments are short and compressing, so which means that any triple consisting of commitment, function, and output may be in the original language of BL20, right? So because there can always be different ways to explain the same commitment by the fact that there exist collisions. So after proposing the definition, we propose a generic construction that combines any pairing-based functional commitment with a special class of verification algorithm that I'm going to explain later, together with a new tool, which is an extractable version of smooth projective hash functions that we define in our paper. We propose a construction of this EPHF scheme based on the discrete log problem under the algebraic group model. And then in order to instantiate our WE for functional commitments, we propose a new functional commitment for the class of circuits in NC1 that has this linear verification property. And the motivation for this new functional commitment was to fill a gap in the state of the art, because essentially all the schemes that could instantiate our construction are in this line, so they have to have this linear verification. But the existing schemes could either support linear mapped or sparse polynomials, and the more expressive scheme instead a kind of quadratic type verification. So essentially, our scheme fits in the first line. And finally, we show application. So we show to realize this succinct version of Mr. Nisic by using our new notion, but also we show other applications to targeted broadcasts and contingent payments. So, and in this talk, for the sake of time, I'll give more details only on the generic construction. Okay, so how does the construction work? So as I said, the first building block is any functional commitments based on pairings in which the verification is you can see it as a linear function in the following sense. So verification algorithm takes the commitment key, the function G, the commitment, the output, and the proof. And then the idea is that verification is linear if you can derive the vector theta and the matrix M. The vector theta is in the target group, the matrix M is in the group 1. And these two objects are independent of the proof. So you can build them only based on the statement, and then the proof is in G2. And then verification just constitutes checking this linear relation. And this is a verification class of verification algorithm that, for example, capture previously existing functional commitments. So then we use this notion of extractable projective hash functions, which is a primitive that works as follows. So they have to work for this class of linear languages, and then this is a simplified version. So, but I think it's okay to get the intuition, which is that you have a key generation algorithm that takes as input a statement. So in this case, a statement of this linear language consisting of theta and n, and it produces two keys. So a secret hash key with which you can hash statements, right? And a public projective key that allows to hash statements, but only if you have a witness for them. So with the property that if this is a good witness, so if theta is m times pi, then actually the public projective hash coincides with the secret key based hash. But if otherwise, like we model security with an extractability like definition. So because the other side would be the fact that if the proof is computationally hard to find, then we would like to say that also it's hard to compute the hash function. And we model this in the following way. We say that for any adversary that given the public projective key can produce a statement and the hash value that is correct, is the correct hashing, then there exists an extractor that finds this witness of this linear relation. Okay, so how do we use this this combination of these two objects to encrypt? And our basic construction is for encrypting a single bit. So the idea is that when you encrypt, so recall you have a commitment key, you have the function G, the commitment the output Y. You don't have X, remember, so you don't have the opening of the commitment. And then the first thing you do is to recover theta and M that come from the verification algorithm. And then you generate this projective hash piece, the secret one and the public one, based on this linear statement. You hash this statement, you get age, and then we extract an argument bit from age. So we do this with a Goldrake-Levin style technique of sending a random R, taking the inner product of H and R modulo 2, and then we do XOR with the message. And that's how we encrypt. So we send along the public projective key, this randomness R, and this one-time part of the message. So decryption is essentially the inverse operation. Like that is that once you have the proof, you can run the public projective hashing, you can get H, and then from R you can recover the secret path, and then you get the bits. And what I can say is that in terms of security, the idea is that if you have a distinguisher for this encryption method, you can run the Goldrake-Levin reconstruction reduction in order to recover H, right? So think that we are extracting an hardcore bit for H. So if you recover H, now we can build an adversary that produces this H. And it was not supposed to do it if the proof was supposed to be like, let's say, computationally hard, because like the statement was wrong. And now if we can produce H, we can extract the proof from this adversary thanks to extractability of the projective hash function, then we can build a reduction to the FC evaluation line. Okay, so let me conclude this talk. So by recalling, so in this paper we propose a new notion of witness encryption for functional commitment. We show realization from simple tools such as bilinear groups, and we show applications that exploit the succinctness property of functional commitments. So in our work, we leave some open problems. One of these is, for example, how to avoid the use of this Goldrake-Levin technique at encryption time. And this would have implication to improve efficiency, but also to obtain an algebraic reduction. This is, for example, relevant to why we have to resort to the GGN. And it would be interesting to obtain W4FC for circuits instead of only NC1 to get schemes from standard assumption, but also to find more applications of this primitive. For example, on this, I can mention that we have a recent work that we published at AsiaCrypt last year, in which we use a special case of this primitive for vector commitments to build registration-based encryption. And with this, I'd like to thank you for your attention, and I'll be happy to take questions.
If you have very short question. I have a quick question. As your construction uses new primitive, like extractable in this project function, I don't feel why the extractability is needed here from the security group. Why you need extractability?
So we need extractability in order to extract the opening proof of the functional commitment. Because the idea is that if the statement is wrong, it's difficult to define why it's wrong, but how to define it wrong. But if the statement is wrong, then the proof should be hard to compute. So we have to find the reduction to the FC security, and we want to get this proof from the hash value.
But why we need knowledge science? Why not?
That's a good question. So since we have to extract something short from like the hash, in principle, we may not need the non-black box extraction, but we couldn't find any way to extract this without non-black box extraction.
Thank you.
Okay, let's thank Dario and go to the next talk.
Thank you.
Next talk. The next talk is beat restrictive relative program obfuscation and its application to MA-ABE, and those are the Kartik Bhushan, Sai Lakshmi Bhavana Ubats, Manoj Prabhakaran, and Rajiv Raghunath, and Rajiv will give a talk.
Please. Hello? Hello? Hello?
It still doesn't work.
If it's making it should work.
Hello. Good morning. So I would like to present our work on reach-restricted reactive program obfuscation and its applications to MAEB. So the starting point of our work is on the sequence of recent work, which all in the face of it look very different primitives, but the underlying techniques was essentially garble circuit chaining. So there was this one-timeness and repeated notion of one-timeness that was these constructions. But surprisingly, there was no common framework, there was no common abstraction, and they all proved from scratch. So we would like to abstract out this ingredient which is driving these prior works and hopefully to get new constructions. And our starting point is as obfuscation. So we want to give some kind of an obfuscation notion that is inherent in these constructions. So what is obfuscation? I'm sure you're all aware. You want to keep secrets in a program, even against an adversary that captures the entire, the program, the computer which it's run on. Okay? This is a subtle, very subtle thing to model formally. There have been very lot of notions of obfuscation, many of which have been shown to be either outright impossible or improbable. And even more standard notions like I/O require strong assumptions in general. So what's going on? But there have also been attempts to look at obfuscation for very specific structured programs and to be able to instantiate them from more standard assumptions like DDH. And in this work, we want to look at the obfuscation in a slightly different way. We want to look at programs that are obfuscated as coming from some sampling that was done interactively. So we introduce like an interaction, and the obfuscation is a result of the interaction. And this somehow we want to say constrains the adversary and helps in guaranteeing security. So to give a motivating example, if you look at, let's say, just public key encryption, right? What you want to obfuscate is this very simple program which has the message in it as the secret. And if you give the secret key, you reveal the message, right? And encrypting the message under the public key is a very naive but valid obfuscation. You can see that like it can be argued that there is both interactive sampling, but you can also simulate. So if the adversary is not given the secret key, then from semantic security, the ciphertext reveals nothing. And if he's given the secret key, he learns the message, right? So our goal is to be able to, use this idea to formalize and to build more complex primitives. So for instance, IB, so identity-based encryption, you could think of as a trusted authority saying, oh yeah, I trust that guy, that's his identity, right? And you want to say, oh, that's just some form of signature and verification. So why can you not look at a ciphertext as saying, prove that you are this identity, and then I'll give you the message. So let's kind of formalize this. So what we're interested in is some form of reactive programs. At a very high level, a reactive program is just two circuits. One is a transition function that updates state, and the other is a message function that releases secrets when you reach a state, right? And you could think of the reactive program as also is. And in this work, we kind of partition the state space into what we call as parts. And we would only be interested in a tree-like state space. And why I say this is because we want to model one-timeness, some kind of one-timeness formally, by saying that it corresponds to some reachability in the state space. Right? So I will say this more explicitly as follows. So our interactive sampling now is as follows. There is a generator G, which interacts with the adversary Q, at the end of which it outputs this program that we're interested in. And the reach restriction is defined as follows. We say that we require an extractor E, which is able to extract the reach of Q, the whatever inputs the Q could have fed to the output program, and the extractor is able to extract this, and it only reaches at most one state in each partition. So there is a one-timeness and it's extractable. The reason I am relaxing this and calling it capital phi is to say that you may not want to extract the full input to be able to uniquely identify the state, to identify the reachability. But yeah. So then what's the obfuscation? The obfuscation is simply as follows. So there is an interaction between G and Q, at the end of which G outputs a program, and then you have an obfuscator that takes a program and obfuscates it. What we would like in the ideal world is for a simulator, which is given only the secrets corresponding to the reachable states, right, as extracted by this extractor, and to be able to output something which looks indistinguishable. Let me give a very quick example of what I mean. So if you think of commitments, let's say standard commitment where you have computational hiding and computational binding, you could think of the interaction as follows. You have some adversary Q, which samples the CRS, if you're in the which samples the CRS honestly, and then sends CRS and this. And now G outputs some program as follows. So it's a very straightforward one-step program. You give the right commitment, it releases the secret. And you can see that this is a valid R3PO, reach restricted reactive program obfuscation, because the only state that could have been reached by a computational adversary is this M, and it is extractable. Right? So if you use a CRS extractor, you replace the CRS generation by some extractable form of CRS, it could have been extracted. So our first result is that if you assume DPH, there exists a commitment scheme and an R3PO for commitment openings. Very simple program obfuscation. You hardwire the commitment, and if you give the right opening, it releases. Think of another example, signature checking, where the interaction is simply Q, the adversary, giving out some verification key and message. It could even be a bogus verification key, doesn't matter. And what the program has in it is this VK, M, and it says that I'll release the secret if you give me a valid signature for this verification key and this message. Again, a very simple program. And we show that if the DDH assumption holds, there exists a signature scheme and an R3PO for it. All right, so we built two very simple programs. Simplest question to ask is, like, can we just use these two to build bigger programs? So for instance, can I do something as follows? I do a commitment opening followed by a signature verification. Note that this is now a slightly more non-trivial setting, because in the first case, if you just see them separately, the interaction in the first case was some commitment. The interaction for signature was VK, M. But what we are interested in the interaction is there is no M. So we want to construct a obfuscation for this program where the message M is not in the interaction. But there is still a one-timeness if you think intuitively, because it is inside the commitment C. Right? So how do we capture this? So to do this, we give a new notion called as decomposition property, and we say that if this big generator is well designed, corresponding to the smaller generators, then given just the obfuscation for the smaller generators, we can build this obfuscation for the big generator. So what's going on here is, in the first case, you have this big interaction, and then you have this JI, which is looking at this big interaction, looking at the big program, and isolate this one small program. And in the other experiment, you have a small interaction, and you have a small J which is outputting a small program, but then you have this capital J looking at it. It can generate the big interaction and the big program from it. And this is what we call as decomposition if the following, if these two experiments are indistinguishable. Given that, we give a composition theorem. It says that if you have all of these G1, G2, Gn with arbitrary schemes, and you now are interested in an obfuscation for G, such that G decomposes to each of these Gi, then there does exist an attribute scheme for G. And the proof is, in addition to other techniques, also uses garbled circuit chaining. The thing to note is that it completely abstracts out garbled circuit chaining. So you no longer need to worry about this kind of labels and keeping track of labels and so on. As a corollary, we get that if there exists an attribute for commitment opening, just a one step, you can do that many times, and you can have an attribute for like a sequence of commitment openings. And this was intuitively what was inside the construction of prior works to get two-round MPC protocols. So if you're aware of these works, they had these garbled circuits which talk to each other. And essentially what these garbled circuits were doing was opening commitments one wire at a time. So you can think of the construction there as simply some obfuscation of commitments and commitment openings. Similarly, if you look at signature checking, if you have a signature attribute for like a one-time signature checking, you can build an attribute for like a sequence of signature checkings where at each step you're checking a different message signature possibly. And it is what was inherent in these IB constructions where you build fully secure IB from selective IB, if you're aware of it. So finally, we show that if you have commitment opening and signature, yes, we can also compose the two together. And this is what allows us to give an instantiation for this variant of multi-authority AB that we call private MAB. So rather than talking about MAB in general, I'll only look at a component of it, which I call attribute verification. So in prior works, they mostly focused on what they call the global ID model, where the setting is as follows. You have a client who has an ID. The servers already know the client, they already know the ID for the client, and they say, these are your attributes. So server 1 comes and says, client, these are your attributes. Server 2 comes and says, client, these are your attributes. Right? And the client has no say in the matter, and you want to do some computation based on it. You see that there is an inherent constraint here in the sense that server 1 doesn't know what attributes server 2 gave to the client. So this is made explicit in their definitions, where servers are not aware of the attributes given out by other servers. And this kind of constraint shows up as the constraint in the feasibility. You only get results in the random oracle model for some very simple class of policies. So what we introduce is, rather than having it as a one-shot, we introduce it as a two-round, where the client says, hey, no, my attributes that I'm interested in are for me to decide, I am interested in X. The servers have some key policy that they have with them. And now what we want is like this two-round protocol for attribute, where the round 1 client sends a request saying, give me keys for X. And then servers send their response to the client. What do we want? So what we want is, one is completeness. If the client asks for an attribute which satisfies server 1 and server 2, so if server 1 is okay with giving the attributes to the client, server 2 is okay with giving the attributes to the client, then the client should get it. What does hiding say? What hiding says is that there is some hiding with respect to the attributes of the client. So the servers learn nothing about the attributes of the client. In addition, the servers and the client do not learn anything about the key policies of the other server. So this is kind of an incomparable notion to prior works, because even though, yes, we do have an extra round, so it might seem weaker, easier to do, but we also have more security requirement in the sense that we also want hiding. And it should be intuitive to see that you can do this by simply doing commitment and signatures. So the idea is as follows: the client commits to the attribute it's interested in, X, sends it to the servers, and the servers send as responses obfuscation, R3PO obfuscations for the corresponding program. So what's the program? It has the C hardwired in it. You give the right opening, it goes to the state M, and it outputs the signature for this server. So the obfuscation for server 1 will release the signature for server 1. And then it takes as input a signature for server 2, verifies that. If that verification goes through, it goes to the next state, releases the secret. So essentially what's happening here is the server 1 and server 2 are verifying each other's signatures within these obfuscations. So it's like the obfuscations are talking to each other. And from our composition theorem and our prior results, there exists a two-round protocol for attribute verification. As a corollary, we get that if you start with any CPAV scheme for general policies, you can immediately upgrade it to this private MAB schemes also for general policies. So note that this is in stark contrast to the other notion of MAB, where results are only known in the random oracle model or under strong assumptions, and for only restricted class of functionalities. So I'd like to conclude here by saying that we introduce a new notion of interactively samplable programs and obfuscation for them. We give a library of simple one-step programs and obfuscations for them and show how they correspond to prior work and the key techniques in prior work. We give a composition theorem to build R3PO for larger programs using R3PO for smaller programs. And this essentially encapsulates and abstracts out the so-called garble circuit chaining. As an application, we construct private MAAB, a variant of MAAB. As open directions, I would like to say that the framework definitely would be useful to have more one-step programs, one-step reactive programs. It is the current notions are already sufficient to capture other prior, such as garbled RAM, which I'll not go into. One interesting feature to add would be the so-called blindness, where instead of doing garble circuit chaining, there are works that do blind garble circuit chaining, where the idea is you don't know whether you evaluated the garble circuit correctly or whether it's just some junk. So essentially, in this program terminology, it corresponds to you don't know whether you reached a valid state or you crashed and reached an error state. So it's like you do a sequence of steps, go through a sequence of states, but you don't know at which point in error. And this is useful in getting notions of anonymity. So for example, anonymous IB essentially uses blind garble circuits. Thank you.
Let me have a big question. So by your new formalization of obfuscation, can we, for example, explain the existing doctrine guard ID instruction, for example?
Yes.
So it's like an instantiation from
so the paper you're referring to, what they use is what they call like one-time signature with encryption, OTSC. And OTSC is essentially what we use in building this one step of signature checking. And then IB is just a sequence of signature checkings.
Thanks.
Thank you.
If there is more questions, then maybe get to the next speaker. Thanks.
Am I audible, by the way, or do you want me to use the mic?
Yeah, I'm just thinking about trying to turn the volume down.
People in the back, can you hear me? Okay, it's good, yeah, because at least.
Use the microphone for the recording.
Oh, okay,
Yes.
okay.
I think it's just a bit over amplified.
Yeah.
Turn it down a bit. Sorry, I don't usually lecture in this room. Can you just hold it a little bit further away?
That's what I'll try.
Yeah, sorry.
Okay. Is it better? No, is it echo? Okay, it's better. Okay. So I thought that probably this will be the talk that will be between the zoo. So you'll probably see kangaroos after this. But it seems like it's probably I'm sort of preventing you from lunch. So I'm between lunch and you guys. So all right. So let's just talk about functional encryption and see. Oh, sorry. My bad.
Dynamic correlation MT and multi-order EAD and also the guard, Risha Koya and the speaker.
Oh, thank you so much. Yeah, it seems like I'm so excited about this research work that I couldn't sort of just telling you more about it. All right, so let's continue. So the story starts of this particular work with function encryption, something that we've seen for almost 2 decades now. And basically, it says the following: it says that there are two parties, Alice and Bob are two favorite parties. And the way this works is that Alice has a master public key and she wants to encrypt some message under the master public key, and Bob has here master secret key. And there's kind of like a weak party over here, Charlie, and Charlie gets some encrypted data. And what Charlie really wants, he says, I don't care about the entire message that you encrypted. All I want to learn is some special information about the message that you encrypted. For example, you want to learn f of m, an evaluation of a function on this message m that was publicly encrypted, or that was not publicly, that was encrypted by Alice. So basically, the idea here is that you want to ensure that we can build an encryption system where Charlie can learn this information, that is f of m, from the encrypted data without actually learning anything about the other message m. And moreover, Charlie wants to do this entire learning without basically interacting with Bob. So there's one simple way to do this is that send all this information to Bob and say, okay, can you decrypt and just let me know what f of m is. We don't want that to happen. We really want to have this outsourced decryption of information where Bob says, okay, I don't want to be online and you still want to learn all this information. That's precisely why the notion of functional encryption was proposed. And basically, formally, functional encryption is kind of defined as follows. So there is typically a setup algorithm. The setup algorithm says, hey, you can generate a master public key and master secret key. Given the master public key, you can encrypt any message M of your choice, get some ciphertext. And now there's also a specialized key generation algorithm. This algorithm takes a master key and breaks it down into some partial function keys, such that when you combine a ciphertext and this partial function key, then you basically learn the evaluation of the function f on the message m that was encrypted. So that's what it means, functionality about the message, functional encryption. So what we really know about functional encryption is that there is one way to sort of just define it formally here, but in terms of security, we really want it to provide some interesting security properties. So the most standard way of defining security for functional encryption is through this indistinguishably based security key. It basically says that consider the following, that there is an attacker and the attacker basically has to distinguish between the following two distributions. Distribution 1, it gets encryption of message M0 and a bunch of these private functional keys which only let you learn some specific information about the message M. And the other side, you switch the ciphertext to encryption of M1. And the adversary basically says, okay, I can't distinguish between these two particular ciphertexts as long as all the functions that I have, they basically evaluate the exact same value on both those messages. So for every fi of M0 and fi of M1 are the same. In that case, there is no trivial information that the adversary can sort of just learn about these two particular ciphertexts that can help in distinguishing these two particular distributions. So it does seem like that maybe FE indistinguishability does carry the right amount of intuitive security that we need for most applications. So it's pretty good. And that's kind of precisely accurate. This notion of security for functional encryption has been very successful. We actually also know that using functional encryption, we can design a lot of crypto through the lens of obfuscation. So it's very well known over the last so many years. But there's kind of like one barrier if you want to view functional encryption this way. The barrier really is that it doesn't exactly capture what we want in practice. And let me elaborate a bit more why indistinguishability based security is not enough. So ideally, what we really want is that an attacker, when it gets a ciphertext, a bunch of secret keys, the attacker does not learn anything about the message M apart from what it learns by running the decryption algorithm. That's what we ideally want. Indistinguishability based security says that you can't distinguish, but it doesn't say that you can't learn anything about the message M more than just by running decryption algorithm. So the most common way of trying to capture this type of security definition is through a notion of simulation-based security, which basically says that given an attacker which has the ciphertext and these keys, that attacker cannot distinguish between the honest distribution versus a simulated distribution, where the simulated distribution only gets an evaluation of the functions on that specific message M. So trying to make sure that maximal amount of information about the encrypted message M has been hidden, has been sort of just kept private. So this is what we would really want in practice, but unfortunately, it's kind of very known that this does go with the goal precisely, but in full generality, simulation-based functional encryption is so strong. And we have very strong impossibility results that they say that you can't build simulation-based secure functional encryption. And the question is, why am I just really explaining you this to you guys? The point is that this simulation-based security simply says that if the number of keys that the adversary really gets to learn, if that is unbounded, then this argument falls through. But can we actually achieve functional encryption in which we can get simulation-based security when the number of keys is bounded? And maybe that has already some interesting applications. So that's basically the main question that we want to study in this work, which is that we want to build bounded collusion functional encryption in which we have the same picture as before, but the difference really is the setup algorithm now gets a collusion bound queue. It basically says that I want the system security to hold as long as only Q keys have been corrupted. So it turns out if we define this object this particular way, then the impossibility results that we had, they basically go away. They don't hold. Moreover, we can actually design functional encryption, such a powerful primitive, from minimal assumption of public encryption. And it already leads to many interesting applications. For example, we can use these concepts to sort of just build or sort of just give a negative result in differential privacy. But there's kind of like one big barrier about bounded functional encryption. And the barrier really is that the collusion bound queue you have to fix at the setup time that's decided for the entire system and you can't change it. Kind of imagine in practice that you set up your system and say, okay, hey, I want to get security against 1 million users. And maybe your system sort of just gets very popular and 1,000,001 users get registered. And after that point, you have to reset your entire system. You can't have any dynamic security. So the question that we really want to sort of study is that can we achieve the best of simulation security, but where there is no pre-decided bound on the collusion bound for how much attack I'm able to sort of protect my system against. So to sort of just address this particular thing, the notion of dynamic collusion model was proposed over the last few years. And the dynamic collusion model basically says that I want a little bit of dynamism in my system. That basically means I do not want to commit to the collusion bound at the setup time, but instead I want this collusion bound to be more like a per ciphertext property, where when I create encryption of a data, at that point I want to say that this particular piece of data is secure against these many colluding users. That gives me as much flexibility as I want in this functional encryption system where I can still achieve simulation-based security and not encounter any impossible results. So prior works, they were able to design functional encryption in this dynamic model from these simple assumptions fitting this exact model. However, those kind of constructions were kind of too complicated. And let me sort of just tell you a little bit more about it. But first, I want to sort of just say that when we go to this dynamic collusion model, and I don't know why it's not appearing in a nice way, but the point is, if we want to sort of just, if we get to this dynamic collusion model, then these limitations that we have for bounded collusion functional encryption, they really go away. Because at this point, the collusion bound is not set up, not fixed at the setup time. And basically, we can adjust the security and efficiency of the system dynamically as we want. So these things go away. So in this work, what we do is we propose a new generic bootstrapping compiler, which basically says that any result that is known in the static model of bounded collusion functional encryption, that can be generically upgraded to the dynamic model. So what you don't need to do is you have to sort of just look at all those last 20 years of research papers, which proposed a new functional encryption system in this bounded collusion model. You don't have to go there and say, okay, I'm going to edit it and make a dynamic model collusion secure. What you can simply do is you can apply a compiler and lift the security from static model to dynamic model. So that's the first main result of our work. And the theorem formally basically says that if you assume identity-based encryption which as we know by now, it's the minimal assumption. It's kind of like a necessary assumption for this particular model. Then you can basically upgrade any static model FE to a dynamic model FE for the same function class. And it basically gives you all the desired efficiency properties. Moreover, it ensures that the scheme is simulation secure. So in the next part, I'm basically going to review how this entire construction really goes. And to that end, let me sort of just here sketch a brief roadmap that appeared in our prior work, in which we basically said that if we want to build dynamic collision FE, then what we can start with, we can start with a simpler object that we call tagged function encryption. And that tagged function encryption was designed from identity-based encryption. So let me first tell you what this tagged function encryption really is. So function encryption is basically this, where there's set up key generation, encryption, and decryption. In tagged function encryption, we basically do the following. We add tags or identities to every element of the system, which basically means that now the key generation algorithm, the encryption algorithm, they both take specific tags as input. And they generate a tagged key and a tagged ciphertext. And then the property is you can only combine two tags, a tagged ciphertext and a tagged secret key together to learn the actual value. But if you combine two things which have different tags, then you won't learn anything. So the tag really is a lambda bit string. And the property, it says that only the ciphertext and secret keys can be combined if T1 is equal to T2, the two tags. And for security, what tagged function encryption says, it says that the ciphertext for a particular tag can be simulated even if security for all other tags has been compromised. So that's the strongest notion of security that you can hope for in this particular setting. So what prior works, they basically said that you can basically take tagged function encryption and you can use that to build dynamic function encryption. So in this talk, I'm not going to sort of just go over exactly how that construction went, but the high level intuition is as follows. The idea is basically we're going to use this tag space to compress an exponential number of master secret keys and master public keys into a really small space. And once we do it, we're going to use some sort of just what we call a linearization trick, which is fairly common in bounded function encryption, and use that to upgrade tagged FE to dynamic model FE. So if you're more interested in how that works, you can sort of just come and talk to me after the talk, or you can read the paper. But the point is, what we know now is if we can build this tagged function encryption, where we can embed tags in the ciphertext and secret keys, then that is enough to build dynamic model collision function encryption. Then the goal is that can we actually sort of just here build this simply as generic compiler? And so as we know, this part is easy. And the prior book said that this part is very, very complicated. They came up with these new designs of tagged function encryption, like really new designs. And they were sort of just starting from scratch. In this work, we really show that what we can do is we can generically take identity-based encryption and upgrade static model to dynamic model via the tagged function encryption. So in the next part, I'm going to tell you how I'm going to take a static model FE and embed tags into it using identity-based encryption very simply. Once we do it, then we can apply this generic compiler from the previous work, and so just that gives us dynamic model FE, closing this entire line of work. So let's just quickly see what are the main observations behind designing tagged function encryption from identity-based encryption. So to really understand it at a very high level, we're going to sort of just do a simple sort of just share kind of like a comparison with prior works. So what I'm going to sort of just do is, I'm going to first tell you that tagged function encryption can really be visualized as a static model function encryption scheme with the following property. The property is, it is really an exponential number of FE systems just joined together. That's how one can view this tagged function encryption system to be. And we also know that identity-based encryption is really public key encryption, where 2 to the lambda, or so just exponential number of public key and secret key pairs are accumulated into a single system. So it seems like there is an analogy that IDE is what kind of like an extension of PKE. Similarly, tagged FE is an extension of static FE, where you embed identities or tags. So our idea is that can we actually take results that we know that can amplify public key encryption to identity-based encryption and use those same ideas to lift static model FE to tagged FE. And that's precisely what we're going to do in this work. So let me sort of just quickly summarize, and this is something that was sort of just mentioned in the last 2 talks as well, that they were sort of just very interesting gardening related results, which said that you can generically lift a public key encryption scheme into an identity-based encryption scheme using these generic gardening techniques that started with the work of Toteling and Gard. And the ideas that they proposed at a high level were that they basically said that you can encode an exponential number of key pairs at the leaves of an exponential sized tree. That's the first idea. The second idea is that you can use a sequence of garbled circuits to traverse this exponential sized tree efficiently in a DFS-like manner. When you combine these two ideas, that means you can basically encode exponential of public keys and secret keys efficiently, and yet during decryption time, you can traverse this very, very efficiently. The point is, an encryptor creates a garbled circuit to defer the actual ciphertext computation to the decryption time. And our idea is basically to sort of just maybe use the same thing, which is we're basically going to say that an ID secret key previously contained an information about a path to a root, and the root is where the actual secret key was there. So what we're going to do is we're going to replace in this entire paradigm each call to a public key encryption algorithm, be it setup, be it ciphertext generation, encryption, or decryption. We're going to replace that call to the appropriate static FE system call. And then once we do it, we're going to use this tag as the IB identity in this particular entire paradigm. That's the high level idea. So in the next couple of minutes, before we sort of just, I think I have about 5 minutes left, or how many?
Yeah. I mean,
5 minutes, okay. Oh, okay. Thanks, yeah, 4.5 minutes, yeah, my bad. All right, so in the next 2 minutes, let me sort of just give you the high level pictorial view of how this construction goes, and then I'll try to conclude. So pictorially, basically the construction works as follows. And again, maybe, I don't know, the formatting is a bit off, but hopefully it all works out well. So pictorially, the way the public key, the identity-based encryption constructions from public key encryption goes is that you basically create this exponential size tree, and at the leaves of this tree, you have a public key secret key pair for a PKC system. That's the basic design. Then what you say is the root of this particular tree serves as a master public key. That's very short. So that's very good. Now, the master secret key, it basically contains an efficient encoding of this entire tree. Not an exponential size, but a very small efficient encoding of this entire tree. Now, the way the ciphertext is defined is basically as a sequence of garbled circuits, where this is the first garbled circuit and this is the last garbled circuit. And the intuition really is that the ith garbled circuit encodes the ith identity bit. And it basically tells you in that which of the leaf nodes or which of the child nodes you have to go to in this particular tree. So a secret key in this particular system, it really encodes a path from the root to the tree. And that path at the end contains a public key of that particular identity. So using this particular garbled circuit chain, you can sort of just start from a generic ciphertext to a particular ciphertext that is encrypted under this special public key PKID that is encoded as part of the ciphertext 1 bit at a time. And the point is that garbled circuits are evaluated one by one, and the last this last garbled circuit, it evaluates, it outputs an evaluation of the PK encryption algorithm under this special public key. And there are a lot of kind of interesting ideas that the previous talks sort of just talked about. That there is a notion of one-time signatures of encryption, iterated simulation, efficiently generating these trees that goes behind the doors of these constructions. But I'm not going to get into that. But what you really need to know is that this particular high-level picture is something that can be executed using known simple cryptographic objects. So what we're going to see next, that I'm going to just make some slight edits to this particular design, and that's going to be enough to build tagged FE, which, as we know, is enough to build dynamic model FE. So our idea is very simple. It's basically to say that let's just replace PKE with FE appropriately. So the first thing that we're going to do is we're going to simply replace. So again, things are flying out of place. But the point is, the first part we're going to replace, rather than calling the public key encryption algorithm at the leaf of each of this tree, we're going to call the FE setup algorithm to sample a FE master public key pair and a master secret key pair at the bottom level. So the tree is basically compression of exponential number of FE keys. Everything else is the same at the top. Then the next thing is that the last ciphertext in this garbled ciphertext chain, it really outputs encryption of the FE ciphertext that is encrypted under the key master public key ID at this particular level. And to create a secret key, we again say that the secret key encodes a tree path from root till this particular master public. So that's kind of like all the same in terms of sort of just how the construction goes. But there's going to be one minor change that you have to make in the design, which is that you have to also use the FE key generation algorithm to actually generate the functional encryption key. Because this entire paradigm only generates this identity-based key to traverse this entire exponential size tree. What we want to do is we want to sort of just do this, but also make sure that we have this functionality property about function encryption. That's where we're going to use the static model FE to give us the right security, but we're just using this tree design to traverse this exponential size tree efficiently. And I would say the rest of the design choices in this entire design are basically natural extensions of what we have seen before. And the proof is also a natural generalization, where at the last step, you have to use the simulation security of the static model FE. So that's kind of like going to be one more hybrid that I have to change in this entire design. And so let me sort of just end by saying that that's the main result. We also have some more results about multi-authority attribute-based encryption. And I think in the interest of time, I don't want to keep you away from lunch. So feel free to talk to me about those particular results as well. And let me sort of just quickly conclude by saying that there were a lot of slides. So let's just go through it. And summarizing our results are that we are showing a generic compiler to go from static model to dynamic model. And the second result is that we are also getting some new results, multi-authority AB, which were not known before, again, from very simple, minimal, low-tech cryptographic assumptions. Thank you for listening. Maybe 0 questions.
So let's have a lunch, and then maybe if you have questions, then go to Mr. Conference.
In this until 1 2. Please go and get your lunch, then bring your